Yes, good morning, children. Yes, we will start at 11:35. I think some more people are joining now. So 11:35, I will start it. So children, are implemented these programs? Anyone? So binary search using iterative as well as recursive, finding minimum and maximum elements in a given list of elements, both in recursive as well as iterative. Linear search using arrays as well as linked list. So next is this Fibonacci series, Fibonacci sequence up to the given number 100, Pascal triangle, right? Totally 53 members are joined. Yes, children. We will start at this 11:35. Children, shall we start? Yes. So now it is 11:35. Total, how many members are there? 2 people are in waiting. You admit all. Right. So we are talking about design and analysis of algorithm, right? So this is the subject with the code 20 ITC 15. right? Already we have discussed about this algorithm. Algorithm is a sequence of steps in order to perform the given task, right? So first, this algorithm is invented by the famous Persian mathematician. The name is Abu Jafar Muhammad bin Khwarizmi, right? So here the fundamentals of our computer science is mathematics only. And most of the algorithms are based on maths only, right? So what are the properties of algorithm? Algorithm must have some input. So it must generate some output. It must be effective, right? So the algorithm must be effective. That means it need to be provide some effective results, definiteness, no ambiguity. Next, finite number of steps. After a finite number of steps, the algorithm need to be terminated. So never goes to infinite, right? So this is algorithm properties which we have studied in the last class. So what are the different algorithmic strategies means brute force. So this is also said to be a trial and error version. So it is also said to be exhaustive methods. So the example for this brute force is linear search and the sorting techniques like bubble sort, selection sort, and insertion sort, right? So now the linear search time complexity is, right. So we can linear time complexity is big O of n, order of magnitude of n. So next to divide and conquer strategy. So when you are unable to solve the problem directly, then we need to divide our problem into sub problems until you need, that this division will take place until all the elements are solvable, right? So you need to divide your problem into sub problems until so it is uniquely solvable. Once it is solved, then we need to combine, so divide and conquer strategy, right? So the which they are working in this means binary search. So the sorting techniques like quicksort, merge sort, and heap sort, so these are working on divide and conquer strategy. Next, the drawbacks of this divide and conquer strategy here is the overlap subproblems. If there is any problem is there, the problem must be overlapping subproblems, right? So in order to address this one, the Bellman Ford, the scientist name is Bellman Ford, what he did, he introduced the beautiful concept that is called dynamic programming. So once you are evaluating something, you need to save in arrays or memory locations. So whenever it is needed, you need to use it rather than recomputing it, right? So in this way, they will solve the problem of overlapping subproblems, right? So this is dynamic programming. So next, a greedy approach, we need to think about optimal solutions. So we can go for this backtracking, branch and bound conditions slowly. We can gradually learn these concepts. So these are the concepts which we have studied in the last class. I asked to implement these programs, children. So what are that programs means? Binary search using recursive and iterative method. So finding minimum and maximum elements in a given list of elements, both in iterative as well as divide and conquer strategy. So next is implement a linear search using an arrays as well as linked list. Linked list, you can go for either single linked list or double linked list. So Fibonacci sequence, recursive Fibonacci sequence generation up to the given number 1000. So make your observations. So next write a Pascal triangle program, then make one observation. By using that observation, you will try to address the problem of dynamic programming, right? So these are the basic problems I am asking to implement. So in this week, please try to implement these programs, right? So next is in the last class also I covered this. So here my program, running time of a program, execution time depends on the basic factors like, suppose if you are running your program, right? So the first factor, it will depends on system configuration. So a system configuration like what is the processor and what is your RAM speed. So whether the processor is i4, i7 or something. So the RAM speed, whether it is 1 GB, 2 GB RAM or something, right? So next is which programming language you are using to implement your algorithm. So next one is which compiler you are converting, which compiler you are using to convert your programming language to its equivalent to assembly level language code, right? Right, mnemonic instructions. So these are the basic constraints in order to um, uh, evaluate how much time is needed to execute a program. But so these are changing from system to system. right? So these factors are changing from system to system, right? So irrespective of these factors, yes. So basically these are the symptoms. These are the symptoms. Irrespective of these symptoms, irrespective of these symptoms, so system configuration, programming language, and compiler, which compiler you are using. So irrespective of this one, so simply you need to evaluate only the mathematical operations, right? So you need to evaluate only the mathematical operations, which operations we are using here, right? So for that purpose, we go for this asymptomatic notations. So symptom are asymptomatic. So here asymptomatic notations. So we need to go for asymptomatic notations. So in asymptomatic notations, what we are doing, so we are talking about the big O notation, omega notation, and theta notations. Theta notations. So these are the different mathematical representation irrespective of these symptoms. So without consideration of these above factors, so irrespective of the above factors, so how your algorithm will be behave, right? So we will talk about big O notation, omega notations, and theta notations, right? So now I will explain what is big O notation, what is omega and theta notations, right? So now before going to that one, these asymptomatic notations, please revision this. What is order of magnitude and algorithm mathematical notations? So now, children, we will go for some samples how this algorithm time complexity we will check it. So already I explained this time complexities. So different problem maybe fall down any one of these categories. So here one constant time. So where we got this constant time? So in linear search, the best case analysis. So the best case analysis in linear search is if you are searching some element, the element is presented at the first position or nearer to the first position. So then the required number of comparisons is the number of comparisons we require here, it is only one. So that is big O of one. This is the constant time complexity. So if you go for binary search, so log n time complexity is binary search, right? So next, if you go for some other techniques, so square root of n. So next is this is a linear time complexity n. So where in linear search, so the worst case time complexity, if there are n elements, so the worst case time complexity of linear search is if the, yes, what is the worst case time complexity of linear search? Children, anyone can speak out. Worst case time order of n. So when it will become, when it will becomes to worst case, when we can say that
when the
that
searching target is the last element.
Yeah, the searching element is present at the last position or nearer to the last position. Yes, the searching element is present at the last position or nearer to the last position, or the element is not present in the list. Three cases. So the searching element is present at the last position or not present in the list or nearer to the last position. In that case, if there are n elements, we need to perform n comparisons. We need to perform n comparison. Time complexity becomes to order of magnitude, order of big O of order of magnitude. Big O means order of magnitude of n. So next is n log n, next time complexity n square. If there is some time complexities like n cube. So can you tell some algorithm which takes n cube time complexities? Yes. Can you tell some algorithm which take n cube time complexities? Yes, children, anyone? Yes, anyone? N cube time complexity. Yes, anyone can tell time n cube time complexity. Yes, children. N cube. So if you go for matrix multiplication in general method, so in matrix multiplication, we are using three for loops now. Outer for loop, inner for loop. Next again we are using some k loop. Matrix multiplication. In that case, we need to go for n cube. So for loop, three for loops. So in that case, so time complexity becomes to n cube. So 2 power n means sum of subsets problem. If you take some set with n elements, if there is a set with n elements, suppose set capital H equal to, so 1, 2, 3. If there are 3 elements, then the number of possible subsets is 2 power n. In that case, 2 power n. These are the time complexities. So what is our intention? If already this algorithm is running on linear, try to reduce it. If it is running on quadratic, then try to reduce it. So in this way, so first of all, we need to analyze some of the algorithms, then we can go for here. So now here, so properties of an algorithm, these are input, output, finiteness, effectiveness, and definiteness. So algorithm constants are patterns. How you can construct an algorithm? So that is sequential. Sequential means one by one, step by step, line by line. So suppose if you want to calculate area of a rectangle, area of a square, area of a triangle, then what we are doing, area of a rectangle. Suppose if you want to calculate area of a rectangle, so rectangle area is L into B, right? Length into breadth. So simply what we need to do, yes, we need to read this L comma B values. So after that one, area is equal to L into B. After that one, print this area. Children are able to see my Word document. Print area. All right. So write area. Right. So simply this one. So next selectional.
Sir, we are unable to see.
You are unable to see. Just 1 second. I will share this. New share. This one. Yeah. So now I think you are able to see my algorithm constraints. Algorithm different constraints patterns. So first one is sequential, next one is selectional. In sequential, just we are following some steps. So in order to calculate the area of a rectangle, the first step is read a length comma breadth. Then you need to evaluate. You calculate this this area. Area is equal to L into B. So next, then once you got this area, you need to print it. So this is sequential, right? In selectional, suppose if you want to check whether the given number is prime number or not. So in this case, what we are doing is the first step here it is reading some number. So after reading this number, then what we are doing, so we are making some selection. So selection, whether this number is divisible by 2 or not. Number is divisible by 2. If it is divisible by 2, that means remainder is 0, then we even, else even. This condition is true, even, else otherwise odd, we are telling. So this is, so that means depending on this number, you are doing some operation. So depending on this result, whether it is even or odd, you are telling. This is selectional statements. You are selecting particular condition, based on this condition output you are going. So iteration means so looping, right? Some looping statements. So I think you are implemented most of the looping, iterative or repetitive statements. Repetitive statements. So next is recursive constraints. So recursive constraints. So already you know this recursive constraints, a function which is calling itself is said to be a recursion. So factorial of the given number, the sum of first n natural numbers using this recursion, factorial of given number. So next, where we are sum of first n natural numbers, sum of first n natural numbers, right? So in these cases, we can go for this recursive methods. So these are the different algorithmic constraints. So in this, what we need to write, algorithm followed by algorithm name. Yes, algorithm followed by algorithm name of your algorithm. So then what are the parameters you are passing, you need to specify. So after that one, you need to write the begin keyword. So if n is 0 or n is 1, what is 0 factorial value? You know this 0 factorial value is, so 0 factorial value is 1. So similarly, 1 factorial is also 1. Suppose if we go for 2 factorial, so 2 factorial is equal to 2 into 1. So 2 into 1. 3 factorial is equal to, so 3 into 2 into 1. Similarly, if n value is 0 or 1, return 1, else n into factorial of this one. So we are calling a function again itself, then it is said to be recursive. So these are the different 4 algorithm patterns. So now, what is the life cycle of algorithm? Algorithm can be any one of these 4 life stages. Designing the algorithm, first design the algorithm, write the algorithm, Once you design, you need to write the algorithm by using this pseudocode or Spark. How to write this algorithm means by using this pseudocode. Pseudocode. By using this pseudocode, you need to write the algorithm. I will tell how to write the algorithm rules in the next class. Once you wrote this algorithm, text whether your algorithm is working properly or not. Working properly or not by using these test cases. So next, analyze the algorithm. Right. So now in this analysis case, so what we are doing, so what are the whether how much it is effective, right? How much it is effective. Effective means, so the prime factors we need to take in the point of time complexity as well as space complexity, right? Time complexity and space complexity. Time complexity here and space complexity. So what is time complexity? The time required to execute your algorithm is said to be time complexity. So the time required to execute your algorithm is said to be time complexity. So whereas the space complexity is nothing but the space or memory requirement. So the memory requirement, the memory requirement to run your algorithm. So which type of memory? This primary memory, the memory. So requirement. So that means primary memory or main memory, primary memory or main memory. To run your algorithm is said to be space complexity. So can you tell some example for space complexity, children? Example for space complexity. Anyone? Yes, children, anyone can tell the space memory requirement for your algorithm. Children, are you there? Yes, children. Yes, anyone can tell the memory requirement, some sample example. So here I am writing some swapping two numbers, right? So in this case, swapping two numbers with and without temporary variable, swapping two numbers with and without temporary variable. Suppose first with a temporary variable. So in this case, what we can do? So swap function, I am calling this swap function. All right, by passing this x comma y and x comma into x comma into y, right? So next, what I am doing here, it is children. Suppose into temp or some t variable I am taking. So t is equal to x. Some t is equal to x. X is equal to y. Right? Y is equal to some t. Right? So here, how many variables I am using? Here I am using three variables. So three variables I am using. Three variables I am using. Three variables using. Suppose here we are using this Java code na. So Java using Unicode. For each variable it needs, assume that 4 bytes. So 3 into 4, 12 bytes of memory we require. 12 bytes of memory we require. 12 bytes of memory we require in this case, right? So if possible, try to reduce the memory requirements. Can you tell children? Is there any provision to reduce the memory requirement here? Yes, anyone can speak out. So here I'm using three variables. So assume that this Java using this Unicode, where C and C++ using ASCII code. So 3 into 4, 12 bytes of memory requirement. If possible, try to reduce the memory requirement. Can you tell anyone? Yes, children, please speak out. Without using temporary variable, without using a temporary.
By avoiding temporary.
Yeah. Control C copy. Yes. Control V without using temporary variable. So what is the logic without using temporary variable? Yes, logic.
A plus B, A minus B, A minus.
Yeah, A is equal to A plus B. So next, A is equal to A minus B. So next, B is equal to A minus B. This one logic without using temporary variables. So take suppose A value is 10, B value is 20, right? So B value is 20. So what we are doing, children, first A is equal to A plus B. A value becomes to 30. So next, 30 minus B. What is B? 20. So this is 10. So this value is given to A. So 30 minus A minus is equal to A minus 30 minus B. B value 20. Is equal to A plus B. So this is B. Sorry. So this is B. This is A. Right. So B is equal to. So now A is equal to A plus B. We did. So B is equal to. So B is equal to A minus B. A is 30 minus B. What is B value? 20. Yes, children, check it. A is equal to A plus B. A minus B will be takes place and stored in B. Okay. A minus B. B is 20. So that is 10. B value becomes to 10. Next, A is equal to A minus B. What is A? A is now 30. 30 minus B. What is B? 10. So now it is 20. This is. So by using some simple mathematical operations, you are try to reduce the memory requirements. But operations, if you go, you need to think for the operations. What are the operations here? So simply in previous case we did only compare swap operations. So in this case, first case, we did only swap operations. In this case, with using temporary variables. So we did only swap. We used only swap operations. Only swap. Right. So now here we go for some these addition operations or subtractions, arithmetic operations. So A plus B, A minus B, A minus B. So one plus operation, two subtraction operations, including the same assignment operations. So this. So we try to reduce the space, but these operations plus and minus operations are increased. Okay, this is the factor. So in this way, you need to think about the memory requirement. You try to reduce the memory. So similarly, if you go for matrix multiplication logic, right? So I think this is very simple logic, matrix multiplications for loop. So this is I loop, right? For I loop, okay, I is equal to 0 something. This is for loop. So next, so for this is for J loop, J is equal to 0. So this is some condition. This is, so next again you are taking one more for loop in this. So for k is equal to 0, k for loop, some conditions. So k step, k increment or decrement, k plus plus. So how many? So loop within the loop. So right. So now this first loop is repeating I times, right? So the second loop is repeating j times. So this third loop is repeating k times. So this third loop is repeating k times. So we are written this loop within the loop. So then we can total repetition is I into j into k. So these many number of repetitions will take, assume that. So if this I comma j comma k are approximately equal to n, then our time complexity becomes to n into n. So that is n cube. Our time complexity becomes to n cube. Right. So this is n cube. How we can write order of magnitude, big O of n cube. Right. If possible, try to reduce try to reduce this time complexity. Try to reduce this time complexity. Here, this algorithm fall down into this cubic algorithm, right? Now this time complexity becomes to order of n cube. So once you look into this one, the matrix multiplication fall down into this. So after n square, there is a n cube like this here. If possible, try to reduce this one, even though by increasing this addition and subtraction operations. So in that point of view, there is a scientist named Stressens. So he did some good mathematics, right? So by using some operations, additions, subtractions, and so on, additions, subtractions, and so on. So he tried to reduce the time complexity becomes to big O of n power 2.81, n power 2.81, right? So this is he's trying to reduce the time complexity. This. So I will explain this concept is said to be Stressens matrix multiplication. How it is possible, I will explain there, right? Right. So now, all right, I will ask some. I will give some examples. Can you tell what is the time required for this one? All right. Next is analyzing this algorithm. We can go for this priori analysis as well as this posteriori analysis. Right. All right. Analyzing this algorithm, it is also contains into this one. Analyzing this algorithm. Analyze the program means, so it uses computer main memory, primary memory, and how much memory cycle, fetch cycles of your processor, right? So whenever you are analyzing this algorithm, you need to take care about 2 points, that is space complexity and time complexity. The space is nothing but the computer memory, that is primary memory or main memory, to hold the data and programs. So as well as this CPU, right? So now here time. So that is time and space, how much time it is needed, how much memory is needed. So these are the two factors in analyzing this algorithm. So next is, suppose in order to analyze mathematical algorithms, sorry, in order to analyze your algorithm, you must be good in mathematics, right? Suppose if you take some cubic equation, n cube 4n square plus 6n, right? So this is cubic equation. So the highest power becomes to your time complexity. Highest power becomes to your time complexity, big O of n cube in this. So if you take this simple cubic equation, the highest power becomes to its time complexity. Suppose if you take some quadratic equation, 8n square plus 16n, in this case, the time complexity becomes to order of n square. So y means the highest power. Where is the highest power? N has the highest power too. So this becomes to your time complexity. Suppose if there is a linear 7n, so 7n expression is linear expression. This polynomial equation is, so 7n, then linear graph, the time complexity becomes to order of magnitude of n. So always we are telling this a big order of magnitude. So order of magnitude is nothing. So priori posteriori analysis, we can go for priori means before developing this algorithm, if you make the analysis, then it is said to be a priori analysis. So priori analysis is better compared to this posteriori analysis. Posteriori analysis means you have developed the code and then you are testing, right? So priori analysis means before developing the code, so you are checking how much time and space is required, this one, right? So before experience, before doing development, so then you are doing this priori analysis. Priori analysis is always preferable. Why means before spending money or some time, then you are making analysis whether it is feasible or not, right? So next posteriori analysis is after developing the code, then you are testing. So after developing the code, if you are testing, if it is not useful, if it is not that worthwhile, then it is waste of your time and space. So the best strategy here it is go for priori analysis rather than posteriori analysis. Right. So now we will take some examples and we will try to evaluate this time required to this one. Right. So now analysis, how efficient in terms of time and space, right? So we are thinking about only efficiency of these algorithms, right? So I am telling this algorithm or this procedure is efficient or not. How it is efficient means in time of space and time only, right? So now it means developing formula or prediction how fast this algorithm works based on the problem space, right? So depending on this problem size, how it is working. So what is this problem size should contains means the number of input output operations, the number of inputs and the numbers of output you are generating, the number of operations involved in this algorithms. So the problem size, so the word problem size here, so you need to highlight this problem size. So problem size indicates what is this problem size. So problem size specifies so the number, that is input output plus output input plus output plus number of operations involved in this. So now the number of inputs or outputs of algorithm and the number of operations involved in this algorithm, right? That is said to be a problem size. Yes. So now you remember this problem size. Depending on this problem size, this word we are using in big O, omega, and theta notations. So time complexity, time taken to execute the program, space complexity, how much amount of main memory requirement to program these executions. The problem size is nothing but number of inputs and number of outputs and number of operations you are doing in that. Right. So next you need to think about order of magnitude of an algorithm. Always we are writing big O, big O, big O. Na? So what is this order of magnitude of algorithm? Big O. Right. So order of magnitude of algorithm is nothing but it is the sum of number of occurrences of a statement in it. Right. So it is sum, total of number of occurrence of a statement in it. That means that particular statement, how many times it is appeared. That particular statement, how many times it is appeared, then it is said to be order of magnitude of algorithm. Children, this point is clear. Order of magnitude of an algorithm is nothing but a particular statement, how many times it is repeated. Right? So that is, it is the sum of number of occurrences. Number of occurrences means counting. Number of occurrences of a statement in it. So now what we are doing, how many times this particular statement is repeated, that is said to be order of magnitude. Children, are you there? Children, is it audible? Yes, please respond. Anyone? Order of magnitude of algorithm is nothing but the sum of number of occurrences of a statement contained in it. Right? Suppose if you take some loop, so for this is initialization, condition, step is increment or decrement step. Right? How many times this loop will be repeated, children? Right? Assume that there are C statements inside the loop. Each and every statement takes 1 unit of time. Right? Here these are, so first statement, second, third, up to so on, C statements. So each statement is repeated, take 1 unit of time. So now first statement 1 unit, here it is 1 unit of time, 1 unit of time. So next second unit is also 1 unit of time. So similarly we have C statements. So total statements is C. So each statement is repeated 1 unit of time. So C into 1 total. So now these statements are, this loop is repeated how many times, children? Anyone can speak out. Yes, children, are you able to see my Word document? Children, please respond. Are you there? Is it audible?
Yes, sir.
Yes. So how many times this loop is repeated? For loop. This for loop is how many times it is repeated? This loop is repeated n times. Here this loop is repeated even though it is less than n, including 0 and 0 conditions. This loop is repeated n times. So actually there are C statements. Each statement needs 1 unit of time, right? So C into 1. So totally C units of time were required, but these statements are repeated n times. So what is that order of magnitude? This is big O of n into C. n into c, we can write it, but c is constant, then simply we can write the time complexity is order of n, big O of n. So order of magnitude here it is the sum of number of occurrences of a statement contained in it. So here each and every statement, how many times it is repeated, simple. Each and every statement, how many times it is repeated, order of magnitude. Suppose next case we are taking some this second example 2. So this outer for loop is repeated n times, inner for loop is repeated m times. Outer for loop is repeated n times, inner for loop is repeated m times. So total number of occurrences is class on the. So total number of occurrences is n into m, right? So outer for loop is repeated n times, inner for loop is repeated m times. So then the number of occurrences is n into m. So here it is, order of magnitude is n into m into c, where c is the constant, you can remove it. So in this way, you need to make the time complexity analysis in general method. All right. So now we need to think about this best case, worst case, and this average case analysis, right? So best case, big O notation, average theta notation. Right. So now I will define mathematically this what is this best case and worst case is. So simply, so you take so mathematical notations for determination of running time of algorithm, right? So what is our intention? Our intention is, so we need to go for asymptomatic. So we don't consider the symptoms, basic symptoms, asymptomatic. Even though if you are not consider the basic symptoms, so by using this order of magnitude, how many times particular statements are repeated, so we need to go for mathematical notation, mathematical representation of some algorithms. So in this case, we can go for big O notation, omega and theta notations. So these are the basic simple mathematical representation. So you need to read the statement is T of n is big O of f of n. How can you read? T of n is not equal to so T of n is big O of f of n. So you read like this. I read it as like this. So T of n is big O of f of n. If there are positive constants c and n naught, so these are the positive constants c and n naught, where n naught is the threshold value, minimum threshold. After this threshold only, particular conditions will be satisfied. So if T of n is big O of f of n, if there are two positive constants, so c and n naught, such that so T of n, time complexity, in order to evaluate your algorithm, the time required to evaluate your algorithm always less than or equal to c into f of n, right, where n is greater than n naught. So this n naught is said to be minimum threshold value. This n naught is said to be minimum threshold. After minimum threshold, suppose what is the minimum threshold? Suppose in first class, so we are telling only introduction class. So you don't consider first class, second class onwards, we have consider the syllabus like that. So n naught, after 1 or 2 units of time only, we need to consider our algorithms, right? So now I will show this time, this minimum threshold value n naught after this condition only. So after this threshold conditions only. So after this n naught value, we can take this threshold value n naught sums up. After this particular interval time only, so there is a clear separation between these lines. So in this, they may merge something, right? After this particular interval of time, so there is a clear separation between these lines. So that means after n value is 2, n0 value is 2, you can consider, right? After n value is 0 only, you need to consider it. Okay, all right. So now T of n is big O of f of n if there is two positive constants c and n naught, such that so the time required to evaluate your algorithm is always less than this c into f of n, right? So this is a simple time complexity. So T of n is less than or equal to c into f of n. So where time T of n is the time required to execute your algorithm. So what is this f of n? F of n is a mathematical representation of your algorithm as a function of problem size n, right? So f of n is mathematical representation of your algorithm. So T of n is nothing but the time required to evaluate your program, time complexity. So f of n is mathematical representation of your algorithm as a function of problem, size n. So what is f of n? We are representing a problem in problem size in mathematical notations like right. So ఏంటి ఆర్ఎం గారు ఇక్కడ నుండి ఉండవు. Right. So T of n is less than or equal to C into f of n. T of n is equal to C f of n where n is greater. Sorry. So children, so T of n is time complexity required to execute your algorithm. F of n is a mathematical. This is mathematical representation of algorithm as a function of problem size here. So that means the time required to execute your algorithm is always less than this constant, right? So this is also said to be big O or worst case time complexity. Suppose the analogy is like this. Suppose in the worst case, suppose I want to come to my college, CBT college from my home. The worst case scenario, suppose I can come by bike or college bus or bicycle or some walk. So in this case, what is the worst case? By walk, it will take more time, right? So that is this is also said to be tighter upper bound, worst case time complexity. So always the time required to execute this algorithm is always less than this one, even though if you take any case, so it must be less than this time complexity, right? So next, omega notation, this is the best case analysis. So this is also said to be least lower bound. So here the same equations, T of n is equal to omega of g of n. In previously I taken the time complexity in function f of n. Now I am taking the this mathematical representation g of n. So time complexity T of n is always same, but the problem size here I am taking in g of n. So g of n is the mathematical representation of your algorithm as a function in problem size n, right? So T of n is omega of g of n if there are positive constants c and n not such that. So T of n, the time required to execute this algorithm is always greater than or equal to c into g of n, where n is greater than or equal to n naught, where n is greater than or equal to n naught. So this problem is said to be omega notations. Omega notation. Simply, the time required to execute this algorithm is always greater than that particular time interval. So next is, so this is worst case analysis, big O notations, big O. Best case analysis omega, and theta notations, this is average case analysis. So T of n is theta of g of n if there are two positive constants. If there are positive constants c1, c2 and n naught such that, so c1 into g1 g of n is less than or equal to T of n is less than or equal to, so c2 into g of n. So always the time required to execute your algorithm is lies between this c1 into g of n and c2 into g of n. So the time required to execute your algorithm is always lies between this interval, this time interval. So for all n greater than or equal to n naught, where n is the problem says n naught is the input threshold value, right? So these are the basic mathematical notations for big O, omega and theta notations. So in general we need to write So in general, we need to write these big O, omega, and theta notations. But in practically, we are writing only. Always we are writing big O notation only. We are writing big O notation only. Big O notation. In general, we are always writing big O notations only. Children, are you there? Yes. Yes. So these are the different asymptomatic notations. So we need to write best case. This is worst case analysis in big O, best case analysis in omega symbol theta. This average case analysis in theta symbol. But in practice, we are writing big O only for this with the best, worst, and average case, right? So these are the simple mathematical notations to represent your problem size in mathematically, right? So you take these examples, so we can use these examples in our mathematical algorithm calculations of time complexities. Children, are you there? Okay, you write down this. However, I will share this documentation is with you in LMS portal. You take these notes from there. Right. Children, are you there? Shall we go for attendance? Think 11:30 to 12:30 in a class. Yes, children, please speak out. Yes, children, are you there?
Yes, sir.
Yes. So these are the big O, omega, and theta notations. So by using these notations, we will try to evaluate the time required to particular algorithms. Here. What? Yes. So children, are you saw this syllabus? In our syllabus, once you see this syllabus, the syllabus. So children, so once no. So once you see the syllabus, children, so first part, unit 1, introduction, algorithm specifications, performance analysis, space complexity, time complexity, aseptic notations. In that big O, omega, and theta notations we will did. So next, searching techniques. In searching, basically linear search and binary search we did it both in recursive as well as iterative methods. So next is sorting techniques. So I will talk about the sorting techniques in the next class, and at the same time I will tell what is the time complexity required to this sorting techniques. Right. Time complexity, time required to execute. So children, this is I make one table to represent, to compare this time complexity of different sorting techniques. So children are able to see my screen: bubble sort, selection sort, insertion sort, quick sort, merge, and heap sort. So these are the different sorting techniques with the worst and best average case analysis. Children, are you able to see my screen? Yes, children. Yes, bubble sort. So what is the best case time complexity of insertion sort? Children, anyone? Best case time complexity of insertion sort, anyone? Best case time complexity of insertion sort. Yes, please. Yes, anyone speak up?
Often.
Order of n, big O of n, order of n. When it is, when, how it is possible? How it is possible?
When the array is already sorted.
Yes, already array is sorted. That means every time we are taking one element, so comparing with the last element, comparing with the recently used element. So if it is greater than the next, we are taking the newly taken element as the recent. So in this way, at the end of first iterations, if the swap operations, zero swap operations are takes place, then so next onwards, no need to go for this again. Next iteration, no need to go for the second iteration. Right. So bubble sort and insertion sort, the best case time complexity becomes to order of n. Right. So quick sort worst case is order of n square. So in this, first three are working on this brute force technique. Next three are working on the divide and conquer strategy. Divide and conquer strategy. Children, are you able to see my screen? In this screen, the first is three sorting techniques like bubble sort, selection sort, and insertion sort working on this first strategy. Next three are working on the second strategy like divide and conquer strategy. First three are working on this brute force technique. Right. Children, shall we go for attendance? Yeah, please respond to your roll call. Where is your attendance sheet? So in this case, you need to practice more, right? If I'm telling something, if you practice only, you will get familiarity in this area. Right. You do more programming. Right, 31st January. Today is 2 by 2. Rule number 1,
Yes, sir.
2,
Yes, sir.
3,
Yes, sir.
4,
Present, sir.
5, 6,
Present, sir.
5 present,
6 present, sir.
5 absent,
Present.
7,
5 present, sir.
yes, 7,
7 present, sir.
8,
Present, sir.
9,
Present, sir.
10,
Present, sir.
11,
Present, sir.
12,
Present, sir.
13,
Present, sir.
14,
Present, sir.
15,
Present, sir.
16, absent, 17, 18,
Present, sir.
19,
Present.
Present, sir.
20,
20 present, sir.
Sir,
21.
17 present,
Okay,
sir.
I will come once again. 21,
Present, sir.
22,
Present, sir.
23,
Present, sir.
24,
Present, sir.
25,
Present, sir.
26,
Present, sir.
27,
Present, sir.
28,
Present, sir.
29, 30,
Present, sir.
31,
Present, sir.
32,
Present, sir.
33,
Present, sir.
34,
Present, sir.
35,
Present, sir.
36,
Present, sir.
37,
Present, sir.
38,
Present, sir.
39,
Present, sir.
40, 40 absent,
Sir, he kept in chat box, sir. 40.
41, 41,
41 present, sir.
42,
Present, sir.
43,
Present, sir.
44, 45,
Present, sir.
46,
Present, sir.
47,
Present, sir.
48,
Present, sir.
49, 50,
Present, sir.
51,
Present, sir.
52,
Present, sir.
53,
Present, sir.
54,
Present, sir.
5,
Present, sir.
6,
Present, sir.
7,
Present, sir.
58,
Present, sir.
59,
Present, sir.
60,
Present, sir.
61, sorry, 301,
Present, sir.
2,
Yes, sir.
3, 4, 5,
Present, sir.
6,
Present, sir.
181,
Present, sir.
1940,
Present, sir.
1940,
304 present, sir.
30,
Present, sir.
304, sir.
okay, I will come.
Sir, 29 kept in chat box, sir.
Just 1
29.
second.
Sir,
Just
69, 17 also kept in chat box.
Sir, 49 kept in chat box.
16 అడ్మిట్ ఇప్పుడే అవుతున్నారు ఎవరు వీళ్ళు శ్రీజ
Sir, 7 present,
Sir, she got disconnected, sir.
So they
One
already
mic
kept in
on.
chat box, sir.
49 present, sir.
16 నెక్స్ట్
17,
Sir,
sir.
49 kept in
sir.
chat box, sir. We
17
disconnected
present,
at last.
29 నెక్స్ట్
17 present, sir. 17 also present, sir.
304, sir.
304 నెక్స్ట్
49 present, sir.
49, sir.
49, sir.
ఓకే 49 44 303 these two are absent. Right, thank you children, please practice it the programs.
Yes. Thank you, sir.